Hey everybody, Mr. Plantt here, and today we are going to go over some of the basic ideas of thermal energy. In class, we've talked a lot about general types of energy this past week, but today we're really going to take a deep dive into what thermal energy is and how it works. All right, so get your notebooks and your pencils out, and let's get to it. So the first thing we need to understand when we talk about thermal energy is heat. Right? A lot of us call it heat energy, but what is heat? And heat really is the transfer of thermal energy from one object to another because of a difference in temperature. All right, so what that means is that a hot object is going to let heat or thermal energy flow spontaneously, so at random, from that hot object to a colder object. That's why when you put your hand over the eye of a stove, it feels hot. It feels like you're getting heat coming up to your hand because the eye of the stove is hot, your hand is cold, and so heat is going to spontaneously flow to your hand. That is the basic idea of heat. Nothing too crazy, but things go from hot things to cold things. Right? The world is always trying to find some balance, and so we're trying to find a balance in heat. We try to find a balance in pressure, all of these types of things. Okay, next big idea is temperature, something that we're probably very, very familiar with. And our definition really is temperature is just a measure of how hot or cold an object is compared to a reference point. Now, the compared to a reference point might be something you're not familiar with. What this means, though, is just that there is some point that we call like freezing, right? So common measurements are Fahrenheit or degrees F, degrees Celsius, and Kelvin. Right, so Fahrenheit, its reference point is 32 degrees. That's the point at which water freezes. Celsius, its reference point is 0 degrees Celsius, because in 0 degrees Celsius, that's when water freezes. And Kelvin is this kind of absolute temperature one because its 0 is when the atoms of a molecule, or not a molecule, the atoms of some object stop moving entirely. Absolute zero. No heat at all. We've never even been able to get there as humans, but we can get close, so it's kind of cool. Now, a thing to remember when we talk about the atoms of an object, they're always wiggling. And so, as we went from a solid to a liquid to a gas, that wiggleness started to increase. So, as a solid, they just kind of vibrated. As a liquid, they flowed by each other. And as a gas, they zoomed all around. Well, if we think about kinetic energy as energy of motion, then temperature and kinetic energy are related. Because as kinetic energy goes up, our temperature also increases. Right? So think about how we get from a ice cube to steam. Right? We have to heat it up, and so those atoms have to start moving faster and faster, which means the temperature goes up. It's called the average kinetic energy. Right? So this relationship between temperature and kinetic energy is really, really important, especially in further on in thermodynamics and other things like that. Okay, next idea is the big idea of thermal expansion. Okay, I like to call it the idea of potholes. So, when we heat an object, we get expansion, thermal expansion. That object expands. And this happens to everything, whether you know it or not. Think about maybe wearing your ring. On a really hot day, your fingers kind of expand out. Your ring expands too, but your fingers expand more, and that ring can be really hard to get off your finger. Okay? But then on a cold day, we get what's called thermal contraction. And that's things getting smaller. So your fingers kind of shrink up, and your ring is really easy to get on and off when it's cold. It's a crazy idea. Also, think about tracks. You notice that on the inside of a track, like a track and field track, there's little gaps. Well, that's because in the summer, the track actually expands, and in the winter, it shrinks down. And so we have to have those gaps there to let the track expand and shrink down. This is also how we get potholes in our road. Water goes down, water freezes, and expands, which is really weird because water is one of the only objects we know of that expands when it freezes, and it's due to the structure of the molecules as it freezes, the crystalline structure. But that constant expanding and contraction and expanding and contraction, that's what makes potholes in our ground. Pretty crazy. All right, so now that we have that idea, the last thing we need to talk about is the three ways in which we transfer heat. And these are conduction, convection, and radiation. Conduction is the transfer of heat through objects touching. So this is like if you have a cast iron skillet on your stove, a metal pan, and you're heating it up for a while and you grab the handle and the handle's hot. That's because atoms are always moving, and when they hit each other, they transfer energy from one atom to the other. So when your hand touches that metal pot, it gets hot. And you, ouch, right? Like this little guy over here, right? The heat is transferred by direct contact. Our next, oops, our next style is convection style of heat to transfer. This is when heat transfers through moving currents in gases or liquids. If you might remember from earth science, things like convection currents, right? The way the method of plate tectonics moving around. And so hot gases and liquids like to rise, kind of like in a lava lamp. Right, you have the heating element at the bottom. It heats up, the lava goo that rises up. As it cools down, it starts to drop back down. And if you see in this picture, we have these little circular arrows. That's because the warm water rises up and the cool water drops back down. We're going to do some labs with this idea of heat mixing and how the warm and cool water move around so you guys can actually see this. But it's a really cool idea. And it has all sorts of crazy applications. Weather, we get convection currents in air that make wind and tornadoes and crazy weather patterns. And it's how tectonic plates move around and why we have mountains and rift valleys and all sorts of stuff. Ocean trenches. Really, really cool stuff. The last method of heat transfer is called radiation. And this is when we transfer heat through electromagnetic radiation. And the cool thing about this is this occurs even in a vacuum. This is why we get we get heat from the sun. Right? It radiates heat to us and it goes through a vacuum, through empty space, and reaches us. So think about like putting your hands to the side of a fire. If you put your hand above a fire, that's convection because the hot air is rising up to your hand. But if you put it to the side of the fire, the heat you feel on the side, that's radiation. That's that heat radiating out to the sides and heating up. It's the same thing that occurs when uranium breaks down. When we have uranium, a radioactive isotope, and it breaks down into, say, lead, that releases heat in the form of radiation. Right? That's how nuclear power plants work. We take that radioactive material, it radiates heat, we use that to boil water, we use the steam to turn a turbine, the turbine turns a generator, the generator generates electricity, and you can charge your cell phone and listen to music while I'm trying to give you guys lab instructions. Pretty cool stuff. Alright, that's the whole basic idea behind heat, right? That kind of gives us our basic vocabulary and some of the big ideas. And so we're going to really apply this stuff over the next couple of weeks and really see if we can dig deep into how heat and how thermal energy affects our everyday lives. As always, guys, make sure you bring your notes to class. We will be grading them in class. Have a great weekend, and I will see you guys on Monday. Bye-bye.